All right, so question, just out of curiosity, what's everyone's major? So I want a response from everyone. So we'll start here and work all the way. Oh, it just almost lasered you in the eyes. So
guys, we're sharing your majors.
So
We're sharing your majors.
I'm double majoring with business administration and entrepreneurship.
okay. Marketing,
Marketing development.
accounting. We'll go up here.
Finance.
International business and marketing.
CIS. Finance and economics.
HR.
HR.
Accounting.
So not a whole lot. Usually have more accounting majors. I'm just interested, just so I know when I'm talking with some of you, I can kind of place you now. I get the marketing crew over here. I like the double major of econ. Honestly, I give this advice to a lot of honor students because a lot of you have so many credits coming in. But I would highly suggest, especially some of you early on, you're like you guys sophomores and some freshmen, like explore the possibility of double majoring, because especially for certain majors, it is not that much additional work. I mean, I've had students sometimes, I was like, it's 2 classes, or it's very, depending on which majors you're thinking about, the crossover can make it not a whole lot of extra work while you're here in college and sets you apart from everybody else who doesn't have that double major, right? So if you're doing finance and you do finance and econ, right? You have all the tools that what you're telling an employer is, I have all the tools this person has plus some other tools, right? Like if I'm accounting and finance, right? I've got all the tools these accounting majors have plus this additional stuff. So I was just kind of curious as I was hearing, not eavesdropping too much, but I hear you guys talking about things. Wow, I wonder what everyone's at. Okay, I digress. So we'll start talking about kind of moving away from we're still using probability, but kind of introduce the next idea, which is that we don't have just like a limited number of outcomes, that potentially our outcomes are vast and even potentially infinite. When we think about an experiment, so up to this point, so if there's 100 outcomes and they're all equally as likely, what if there's an infinite number, or whether we have some functions that give us these probabilities. So we start to think about what we'll call random variables, right? So random variable is just any variable where we don't know what the outcome or what the value is going to be prior to kind of running the experiment. But we know that there are a set of outcomes and they're all more or less likely. So we're going to have 2 different types, which are discrete and continuous. So discrete random variable is going to be one in which the outcome can only take on integer values, right? Or not necessarily integers, but there's going to be gaps in between. Right? Continuous is the same idea that we had before, where it could really be any value, right? So that definition doesn't really change. It's just now, instead of thinking about a variable existing in a data set, we're thinking about like a random variable, something that we're going to record the outcome of over time, right? So it's something that hasn't happened yet. That's the only real difference. Right? So we usually kind of use this capital letter X to just notate, whatever this random variable X is that we're interested in, right? It could have a bunch of different outcomes. So these different outcomes, right? We're gonna, somehow realize, this experiment is run, and we'll record like X subscript 1. That'll be the first outcome we saw. X subscript 2, second outcome, so on and so forth. So we'll be using X's now. So discrete random variables, like I said, I'm going to fly through this stuff basically things we've already talked about. The only difference is it's not a variable in a data set. It's just something that's going to happen in the future that will record basically into a variable. Right? So it's just a little bit different. So discrete random variable, usually it's a small number of responses. We've talked about this before. If we think about a number line, it's only the integers, it's not the values in between. Right? So we went through plenty of examples of this, right? How many times did you do something the last week? We'll hit it once, and twice, and you can't do it 1.5 times, right? A continuous random variable, same idea, but we can see all the values in the interval or in the in between the integers, right? So I could see 6.354. So we've already kind of talked about this, we can think about income, interest rates, right? These are going to be continuous, right? I can see out to any decimal on the interest rate on the loan. So some typical ones you might think about, if I have this random variable of family size or the number of dependents that they put in their tax return, right? I can think of this as going to be, I can't have half a dependent, I either have 1, 2, 3, so discrete. The distance that you might be from home, right? So let's say I choose a person at random, what's the probability that the distance from their home to some store that I'm interested in is 100 miles, right? Like the distance to the nearest grocery store. Well, probably it's 100 miles, probably not very likely, but the probability it's 0.7, probably a little bit more likely, right? So I know that I could see any distance, but they all have different probabilities associated with them, right? So that's going to be continuous. I could see, as long as I'm measuring the distance pretty accurate, I can get out to whatever decimal I really want. We'll often see this. So once we start dealing with these random variables, we kind of lose the ability to really do much with qualitative variables. Other than I can basically convert a qualitative variable into a discrete variable. So here, I ask someone like a survey question, do you own a dog or a cat? If they respond no pet, only dog, only cat, or both, right? Well, those are qualitative responses, but I can code them as numbers. So now when I say, well, what's the probability for this random variable? I see a 1. What that's really telling me is what's the probability that the person doesn't own a pet, right? So we can use qualitative variables still. We just have to kind of force them to be discrete, right? Represent them with numerical values. Excuse me. Yeah. Questions on this? Shouldn't be anything tough or anything really that new yet. So we've got all these different outcomes that we could see for X, whether it's discrete or continuous. And before this exam, we will next week, we'll probably, I haven't decided yet. I might introduce one continuous distribution to you. If I do, it's pretty easy, but for the most part, we're going to be focusing on discrete random variables. Okay? So when we have a discrete random variable, we have all these different outcomes that it could take on. We're going to have kind of something we call a probability distribution. So when we had the actual data, we came up with a frequency distribution. I looked at the data and I counted up the number of responses I saw of each different type. Well, now it hasn't happened yet, right? I haven't, I'm not looking at the data, but I know that different outcomes have different probabilities of occurring. So we can basically do a very similar thing, like a frequency distribution, but it's like a projection for the future, right? And that's going to be our probability distribution. So we can do the same kind of things with tables. We can put them into graphs. But more importantly now, we're going to have an actual function a lot of the times that gives us the probability of seeing different outcomes. Okay? So this function is what we're going to call the probability mass function. So it looks similar to what we were doing when we had the way I have it written now, as we were doing with probabilities. But the probability mass function, when we write it out, is going to look something more like this. So I've got my random variable x, and I might want to know, okay, what's the probability that x is equal to, I don't know, the value of 2, right? And then we have some function with this x in it, we plug in 2 for x, and it spits back out at us the probability, right? So it's almost like, right, we've got some function f of x. If you've taken other math courses, right, that's typically how we write functions. It's just now, because the probability mass function, instead of f, we're going to use that p. Okay. So using this function, we can find the probability that I see 0, probability I see 1, probability I see 2, so on and so forth. So it looks something like this. So once I'm interested in different outcomes for x, 0, 1, 2, 3, if it's discrete, I can plug those values into my probability mass function, and it spits back out at me what that probability is. Well, basically now I've got x, y pairs, right? I've got all my x values and my y value, essentially the probability that I see that x value occur. So I can graph these, I can do bar charts. It's not, once I have those 2 coordinates, I can do everything I was doing before. We know that this probability mass function has to be representing the probability of seeing something, so it has to be between 0 and 1, right? This is nothing real new. Similar to things we've already done as well, if I looked at every single possible outcome, right? So starting with the first outcome, going to the very last possible outcome I can see, if I add up the values that this probability mass function spits out at me, well, I know that that's the probability of every single possible outcome. So if I add those all up, I should get the entire experimental outcome space of 1. Right? So this is really similar to the things we've done already as well. Right? These are just kind of a little bit different notation because now we're applying them to a slightly different scenario. The cumulative mass function is the same idea that what we're doing with cumulative relative frequencies, right? So it's going to be the probability that this random variable x takes on a value of 3 or anything below it, or the probability takes on a value of 8 or anything below it. Right? So one thing that's kind of nice, at least for now, when we're dealing with these discrete random variables, is if I want, let's say, I've got this cumulative mass function, and I want to know the probability that something's less than or equal to 3. Well, every single outcome that I can see is actually mutually exclusive. And the idea that, let's say I'm interested in the number of kids in a household, I either have exactly 3, or I have exactly 2, or I have exactly, like, I can't have only 2 and only 3 kids. That doesn't make any sense, right? I either have 3 kids or I have just 2 kids. So there's no overlap, right? So if I think about it, I can just take every single event that's in here and there's no intersections. So before we said if I wanted the union of 2 events, that was add up the probability of the 2 events, subtract out their intersection. It gets a little more complicated if we want to do this with more than 2 events. But the idea if they're mutually exclusive is that it doesn't matter how many events I want. If there's no intersections, I'm just adding the probabilities up of every single outcome that's I'm looking for, the union of. So here, the probability that I see 3 kids plus the probability I see 2, all the way down to the very lowest possible response we could see a lot of the times for these discrete variables is 0. Right? But this idea that once I see an outcome like these different values for the outcomes are mutually exclusive. I either see exactly 3 kids in a household, exactly 8 kids, So that's going to be quite often we get our cumulative mass function by using our probability mass function multiple times and then adding them all up. Sometimes there's a nice neat function, but really that doesn't happen until we get to continuous random variables. So for discrete random variables, there's not a nice cumulative mass function. The cumulative mass function is us kind of adding up several uses of that probability mass function. So it's cumulative mass function as we get to higher values, right? Should be getting closer and closer to 1. If you think about it, I said, what's the probability someone has, 20 kids or fewer in their household? Probably is almost 1, right? I mean, I don't know anyone that's got more than 20 kids, right? As I get closer to, smaller and smaller values, that cumulative mass function is going to get closer and closer to 0. And this is the same idea of that cumulative relative frequency. Okay. So I used some, Purdue football data at one point to kind of build up this. Really, this is an easy example. The more interesting stuff is once we kind of go to binomial and ECON. So, maybe I've got, based off of historical data, I look at all these different number of wins. I have the, sometimes fortunate and unfortunate of being a Purdue football fan. So I can look at how many times they have 0 wins, only 1 win, only 2 wins, so on and so forth. This is going to be exactly the same thing we did with relative frequencies. It's just got different names to it. Because looking at this old data, I'm going to say, okay, based off the historical data, the probability that this team wins, 7 games this year, well, 5 of the last, you can't see it because the Zoom thing's covering it, so. Oh, get out of here. Can I move this? I should be able to move this. There we go. 5 of these 35 seasons that I had, right? They had 7 wins. So the probability that they get 7 wins, I would say would be 5 over 35, or ends up being 0.14. Okay? So it's the same thing we did before, right? We're just going to take every frequency divided by the total number of observations. And now instead of relative frequencies, we're basically going to use those relative frequencies as our projected probabilities of seeing different outcomes for X. Okay? But remember, it's still like projecting, right? We haven't realized it. Based on historical data, this is what we're projecting. If we add up the probability of every single possible outcome, we should get 1. Right? Same idea as what we're doing before with relative frequencies. Nothing's really looks that much different. There we go. I could put these in a graph. Same thing we were doing before. I've got my different outcomes for X, and I just draw the bar up to whatever the probability I see that outcome is. Right? Same idea as relative frequencies. Really nothing new here. So what if I want to find the mean of a discrete random variable? So if we're thinking about my discrete random variable here has what? 0 through 12 as the possible outcomes, different probabilities associated with each outcome. If I was going to find the mean, like number of wins, right? So remember X here represents the number of wins. What do you think this is going to look really similar to something we've already done before? A weighted mean. I've got all these different outcomes for this, or this X value to take on, but I know some of them are more or less likely, so I'm going to want to weight some of them more than others. Basically, my probabilities become my weights. Okay. Oop, I forgot a marker. So if I'm thinking about the mean of one of these discrete random variables, let's think about if I use the X values, now my weights are the probability mass functions for the different X values. And then I divide by the sum of my weights. My weights are these probabilities. What should the sum of those probabilities be? 1. So I can ignore the denominator. It's actually like a weighted mean, but easier, because I don't have to worry about adding up the weights now. I think I even kind of showed you with some of the weighted mean. Instead of dividing by the sum of the weights, you could like convert it to make it like instead of using the frequencies of 10 and then the sum of the weights, which was 50, you could do 10 over 50 times the first X value. And then maybe 5 over 50 times the second. That's basically what we're doing here, right? Because we've created these probabilities. We turn those frequencies into probabilities, and then it essentially makes our weighted mean equation a little bit easier because we always know, right? There's the sum of the probabilities will always be 1, so we basically end up with the weighted mean with no denominator, right? So pretty easy. It's nothing like different from what we've done before. One small difference might be terminology. So when we're finding the weighted mean of a variable, right, so we're taking the actual values. Well, now this weighted mean that we're finding is really going to be an expected value, right? It hasn't been realized yet. Based off of the probabilities of seeing different outcomes, we can project what the future value of that X variable is going to be, right? But it's still like an expected value. It hasn't been realized yet. It's calculated using probabilities of different outcomes occurring. So like the most basic example of this, I think I probably won't be able to do this math in my head, but it's a fun example. So let's say I'm looking at a lottery, right? And I can see like 2 outcomes. I spend $1 and I don't win, right? So my payoff is -1. Or I spend $1 and I win the million, right? So I make what? $999,999. However, I know that the probabilities are very different. So maybe the probability is like 0.0001 here, and so 0.99999. Well, how do I come up with the expected value of playing this lottery? Here's my X value. Here's my probability that I see these different X values. It's just multiply each probability by its value, so 0.99999 times -1 plus 0.00001 times 999,999, right? So hopefully I chose a small enough probability here. But the interesting thing is if you have like this skew, this is kind of a little bit of an aside, right? Even though the loss is only -1, because it's so likely, right? And the outcome of $1 million minus the dollar it took you to buy the ticket is so unlikely, right? But this expected value of playing a lottery almost always, right? So if I think about this as my expected value, it almost always ends up being negative. Right? So even though you have these really large prizes, because this probability is so small, if you find like the weighted mean, the expected value of playing a lottery, it's almost always negative. Right? There was like now I don't have anything for it, so you just have to take me at my word. I think this was like 3 years ago or 4 years ago, though. there was whatever the big, Powerball lottery is, it had gotten to a high enough prize total if you won the big prize, won the lottery, that it actually had a positive expected value, like the first time in the history of that lottery that there had ever been a positive expected value for playing. Which meant the rational thing to do was for everyone to buy a ticket, right? Because you had a positive expected value of making this investment. Although I caution calling it a lottery investment, but that's the idea, right? So in finance and stuff, we'll talk about these expected values all the time, trying to make projections for the future. That's really all we're doing here with finding the mean of a discrete random variable. Right? And we already talked about the sum of the weights is 1, so that's why it kind of makes our equation a little easier. So if we can do like a weighted mean, what do you think we can probably also do with this discrete random variable? Let's skip that. We can also do the variance. I'll come back to that slide in a second. So the variance is going to be basically the same idea of what we were doing with the weighted variance. So we'll take the deviation from the mean, square it, multiply by the weight, which for us now are probabilities, add them up across every single possible outcome. But now instead of having to worry about dividing by the sum of the weights, well, the sum of the weights, or weights or probabilities, will always be 1 as well. So it's almost like it makes our mean and our variance equations easier, but it's like we only have to use the numerator part from that weighted mean, weighted variance equation. So same rules apply. Once I have the variance to get the standard deviation, just take the square root, right? Nothing new there. So I can think about how could I, from that data set, calculate both of these, right? Like I said, this is really going to be almost like review. We've really done problems exactly like this. Okay? So for the weighted mean, I can see some of you writing, so I'm trying to hold off here a little bit. But if I want to find the weighted mean, all I'm going to do is go through the data, take each x value, multiply it by the probability it occurs. Now here, if I'm wanting to save myself a little time, I can ignore the outcomes that have a probability of 0 occurring, right? So this is the idea that these outcomes based on historical data won't occur. So they shouldn't be influencing the mean at all. So anything times 0 is just 0. We could almost ignore it, right? But to be kind of complete, I could write it out for every single possible outcome for x, multiply each one by its probability of occurring, and that would give me my mean, right? So the expected value any season for Peru based off of historical data is that they get about 5 minutes. This is a thing I can tell you is fairly accurate. Right? Usually they're kind of floating around this level. Okay. Now, if I want to do the variance, right? I now have my weighted mean. I'm going to go through every single outcome for x, subtract that weighted mean of 5.14, square it, and then multiply by the probability that I see that x outcome occur. And then add them all up. So I go through 0 minus 5.14 squared times 0.00. Well, I could have ignored that one, right? That has 0 probability of occurring. 1 minus 5.14 squared times 0.06. Keep doing that for every single possible x outcome, add them all up. This is a unique example where I get a variance that's actually kind of similar to the mean. It's just the way the numbers played out here. Okay? But like, this process looks nothing different than what we were doing before the variance. Okay? Any questions on this? I'm just going through this a little bit quick, but because I like the other stuff we're going to talk about, and I kind of find the general setup a little bit repetitive. We've already done stuff like this. So usually I give you guys a little bit of time to work through this. I'll kind of leave these up here, and if you want on your own, kind of go back and try to reproduce these numbers, because this isn't wildly different from the things we've already done. So if I had these different x values, so this was like a bonus amount, right, in millions, so 10, 6, 3 million, or 0. The probability to get a $10 million bonus here, this huge company is 0.15, 0.25, etc. How do I find the weighted mean? Well, first of all, it's kind of like the weighted mean. Like, if I'm looking at these outcomes, right, for the expected value to be 250,000, what would have to be true about these probabilities that isn't, I guess? I think about these probabilities are our weights, right? So if something's more likely to occur, that should be influencing that expected value, that weighted mean, a lot more. So if the expected value was 250,000, right? And these represent millions. What would have to be true? How would these probabilities have to change? What would they have to look like for that to be the case? These would have to be smaller, and the probability of saying 0 would have to be quite a bit higher, so that it would be pulling that expected value down, right? So this doesn't really make a lot of sense for us. And I'm looking at these, the one that's going to influence it the most is 3, right? If I'm somewhere in the middle of all these, this still isn't like the lowest point. It's probably between 3 and 6. I'm probably going to guess C or D here. I don't know until I actually go ahead, take the x value of 10, multiply by 0.15, add to that the x value of 6 times 0.25, so on and so forth, add them all up, and I get, well, I don't think I have it up there, but we get 4.2 million, right? So kind of here we've got an additional check. You've got that 4.2 million, should be what you come up with if we actually go through the calculation. Then if I wanted the variance, how would I do that? Well, I've got the mean now. So I go through, take the first outcome for x of 10, subtract 4.2, square it, then multiply by the probability I see that deviation from the mean occur, 0.15. Add to that, 6 minus 4.2 squared times 0.25. Do that for every observation. Which of these answers make no sense? Yeah, if I'm finding a variance, same rules apply. It has to be positive. Every time I take a deviation squared, that's a positive value, right? So automatically I know like this makes absolutely no sense, right? Probably unlikely that we would get the same value for the variance as we get for the mean too. So 4.2, if I'm guessing, probably could rule that out, right? Oop. So if I go through and compute this one, I believe the answer you'll get is 9.96. So I'll re-upload these and then kind of put a little circle around those two answers. We should be getting 9.96 and then 4.2 million. Where are we at with Tom? Okay, perfect. So there's some additional problems if you want to work through them on your own. Does anybody recognize this movie, by the way? Okay, so you should all watch this movie. It's called The Big Short. Yeah, so this is like basically kind of outlines the financial crisis, like as kind of being someone in economics. I thought probably the best job of breaking it down to like non-even business related like people, like my sister, who I describe as like this bohemian hippie, like she's living in an Airstream for like all the last 5 or 6 months, like she's doing her own thing. She saw this movie and like loved it, right? And she understood. It was just like, oh, it makes a lot more sense now. I was like, yeah. So great movie, good actors. I always mention at this point, right? And coming out of business school, like you're going to get potentially even in interviews and stuff, people might ask you questions about like things like the 2008, 2009 kind of recession, right? And I have a little bit of knowledge just to be like able to discuss. So where are we at? I'm going to introduce this next idea to you, which is I kind of show you general random variables, but we're going to be more focused on discrete random variables that follow certain, I don't call it patterns, but follow a certain structure. Right? So anytime that we have some experiment, right, that has an unknown outcome, and we're doing it n number of times. So we keep running this experiment and we do it n number of times, right? If the outcomes are, the options for the outcomes, there's only 2, right? So we can define the outcome as either a success or a failure. Now, when I say success, one of the things we could be looking for is something like, what's the probability that we see 5 car crashes out on this specific road, right? And I want to make sure I have enough EMT and personnel. Well, the thing that I'm looking for is how many car crashes I see. That's not a success. It's just that when we say success failure, it's basically we have the thing we're interested in finding the probability of, and basically it's complement, right? So either a car crash or not a car crash. So if we have 2 outcomes and we run this experiment n number of times, and the probability of success in any one trial is the same. Right? So I could also phrase this as a real simple game, right? Flipping a coin. I can flip a coin 50 times, and it would be 50. I either see heads or tails. So maybe I'm looking for the probability of seeing different numbers of heads. So success is seeing the heads come up. The probability of success on every coin flip is 0.5, right? The probability of success is the same across every single time I run this experiment. And usually in order for that to be true, we need our trials to be independent. So if I get a heads on the first coin flip, it doesn't change the probability that I get heads on the second. Okay? So that's the idea that they're independent events. Right? So as long as we have this set up, we've got a very specific function that will give us the probability of seeing different numbers of outcomes. So if I flip a coin 50 times, I can say, okay, I'm out of those 50, what's the probability that I get 20 of them to come up heads? And there's a very specific binomial function that will spit out at me that probability of out of 50 trials, what's the probability that 20 of those 50 are heads? So how many successes in n number of trials? That's essentially what this probability mass function for the binomial distribution will tell us. Okay? So it's going to look something like this, right? So it might not look real pretty at first, but it has like three moving, like changing components. One, well, what's the underlying probability of success on any one trial? So flipping a coin, that p-value would be 0.5. Right? The probability on any one coin flip that I get a heads is 0.5. We then plug in x, right? I'll do n first. N is just the number of trials. So if I'm flipping a coin 100 times, n is 100. If I flip it 73 times, n is 73. And then the final thing is x, and that comes from what number of outcomes we're trying to find the probability of. So if I flip a coin 50 times, and I want to know what's the probability that 20 of them come up heads, I can find the probability of this random variable x, right, takes on a value of 20, and then I'm just plugging 20 into my x in that equation. So this part should be math we're comfortable with, right? Hopefully we can like take the difference between 1 minus this probability, raise it to a power, right? This isn't like anything new, but these factorials might be something new for some of us. So does anybody know what a factorial is? Yeah, you're the first one.
So if it's like 10 factorial, it's like 10. Or the time.
Close, yeah. So if I have 10 factorial, you start at the value to the left of your exclamation point, and you multiply all the way down to 1. Right? So, that's the only other thing that we don't know in this equation. As we work through problems, I'll talk more about that factorial and some issues like with it and some ways we can get around it. But for now, just know that x factorial means start at x, multiply all the way down to 1. That's not the most technical way of saying it, but that's the easiest way to think about it. Right? So we've got everything out of the way now. We know every part of this equation, right? The 3 components plus now this idea of factorials. And here's like the formal one. Oh, some things I'm glad I put this on the slide. I would have forgot. One weird thing here is sometimes 0 presents us with some weird issues in that. 1 factorial and 0 factorial are actually treated the exact same, right? So 1 factorial and 0 factorial are both equal to 1. Also, I'm sure all of you know this, but if I take anything to the 0 power, that's just 1, right? So that makes our life a little bit easier as well, knowing those 2 things. Okay. So let's say I flip a coin 10 times, and I'm interested in the probability that it comes up heads 4 times. Okay. Well, what would my x be here? Remember, x is the number of successes we're interested in. N is our number of trials, and P is the probability of success in any one trial. So here, our underlying probability of success on any one coin flip would just be, usually it would be 0.5. But here in this example, we have, I forgot to read this part, but we have like this unique coin, right? That's a little bit weighted. So it only comes up heads 0.4, the probability of 0.4. The probability of success on any one trial would be 0.4. The number of trials we have, n, is 10. I'm flipping the coin 10 times. And I'm trying to find the probability that it comes up heads 4 of those 10 times. So my number of successes I'm interested in finding the probability of would be 4. From there, it's just a matter of plugging those values into our equation. Right? Once we identify those, it's just plugging those values into this equation and being comfortable doing this on our calculator. So to be comfortable doing it on your calculator, the easiest way I would kind of say is don't do the easy math in parentheses first. Like instead of entering this all in one line of your calculator, hopefully we can look at this and say, okay, this is actually 0.6 to the sixth power. So 0.6 to the sixth, hit enter, times 0.4 to the fourth, right? So you could like break it up into calculate this value, and then calculate that value. If you want to do it all at one time, it's fine. It's just a little bit tricky with the parentheses sometimes. Yeah, this is the basic stuff, right? And that function is always going to give us the probably as long as it meets that binomial distribution criteria, right? Two outcomes, identical trials, we can always use this form. Any questions on that? Yeah.
There's no way you can do that just like on a standard regular calculator, right? Or just do it.
A factorial?
Yeah.
Yeah, so usually I've only had like, I mean, if you have a dollar store calculator, no, right? Like if you, there is a threshold, right? But I think like any scientific calculator, like financial, usually there will be a button, and sometimes it's like you can actually find the factorial button, which on a like TI 83, there's usually like a math or a PRB or a probability button, or it's going to be under, like I said, like a math button, and then you move over to probability, and you can find the factorial button. If you're having problems finding it, like everyone's has a slightly different calculator, let me know. But yeah, I think it's like second math on like the TI above 80s, and then you move over to probability, and it's one of the options there. Sometimes it'll be like second, and it's actually one of the buttons on there. Yeah, like I said, every calculator is a little bit different. So if you're having issues finding it, feel free to reach out to me. Maybe try to Google search it first, because usually that's going to be what I'm going to do if you tell me the type of calculator you have. But yeah, usually you can find that button somewhere. Any other questions on this? So I want to introduce a couple things about the binomial. I'm trying to think of where I want to go. I'll do it now. So what if, think of a couple issues. So even if you find that factorial button, let's say I've got something that's very likely to occur. So the underlying probability of success is something like, I don't know, 0.95. And I'm doing this experiment 100 times, right? So I don't know, maybe this is the probability that, let's get it on top of 0.95. So if I chose someone at random, what's the probability that they find whatever sister Cindy or whatever name is funny? So we'll use that one. I ask 100 different people, right? What's the probability that I see 99 of them, right, respond with it, they think she's funny. So here's a problem. I start plugging in my values, right? So I want to find the probability x is equal to 99. So n factorial over x factorial, n minus x factorial, and then all the other stuff. And I just want to focus on the factorial part, right? If any of you have found that factorial button in your calculator, what happens if you try to put 100 factorial into it? It can't do it, right? This is an obscenely large number, right? So this is one of those situations where it's great that we have computers and like these things in our pockets that have like the internet and like you can get like a pretty high powered calculator on your phone. The issue is sometimes we don't see some pretty common sense stuff. You can't do it. You can't do 100 factorial. Like my calculator doesn't do it. Well, no, your calculator just doesn't have the power to do it, right? But your mind has the power to do this very easily, right? If I think about what 100 factorial is, all the way down to 1. 100 minus 99, that's just 1 factorial, so just 1. Right? And that 99 factorial is 99 times 98 times 97, all the way down to 1. Well, notice, everything past 99 is going to cancel, and I've got 100 over 1. All this expression is 100. Right? So if you try to enter it in your calculator like this, it's going to yell at you, you can't do it. But if we just think about what the factorial is, sometimes there's these ones where we can, cancel almost everything out and do it by hand when our calculator couldn't actually do it. How many times have we run into that problem? But that is one of those situations. Any questions on this? Okay, so let's say I've got another example, right? Where I've got what? Probably any one person has a college degree is going to be 30.3, right? 30%. If I ask 5 people, right, and maybe I'm like doing something like taking a small sample, and I want to make sure that, you know, I don't have an overly educated sample or an overly undereducated sample relative to the population. So I say, well, look, if I select 5 people, excuse me, at random, what's the probability that 3 of them have a college degree, right? That's ideally what I would like. So I want to see if that probability is relatively high, then good. If it's not, then, you know, I might have an issue with my study. So here, what's my underlying probability of success? Yeah, probably if any one person has a degree, 0.3. How many people am I asking? And I'm interested in finding the probability that X is 3. Right? This is what I'm interested in. So that makes my X value 3. At this point, it's just a matter of plugging those values into that binomial. Right? But before I do that, I can kind of start to think about values like make sure I don't make an egregious error. Right? And I'll choose a slightly different number to start. So let's say I have that same probability of 0.3, but instead of 5 adults, I ask 10. Right? Out of 10 adults, what do you think would be the expected value or the most common value to see, or the number of successes you would see out of 10 individuals? 3, right? If the probability of success in any one person is 0.3, and over 10 people, on average, we would expect to see 3 people have the degree. So I'm kind of jumping ahead a little bit, but if we want to find the mean for a binomial distribution, what you did in your head there was basically just take that underlying probability of success in any one trial and multiply it by the number of trials you have. So here, if I've got 5 people, how many can I expect on average will have a college degree? 5 times 0.3 or 1.5. Now, this is where it gets a little tricky because can I ever actually see this value? This is discrete, right? We're still dealing with a discrete random variable. So I could see 1 person of 5 or I could see 2 of 5. So if I come up with a mean and it's not a specific integer value, what it's telling me is the most common outcomes. So if I think about here, I've got my X values, and here I've got my probabilities. I see those different X values. When I see a mean of 1.5, that's telling me that the values to the left and the right, 1 and 2, will be the most likely outcomes, right? Because out of 5 people, on average, I would see 1.5 have a college degree if the probability any one person has is 0.3. So if I start to move away from that point, I was making sure I wasn't holding that past point. If I start to move away from 1.5, what do you think is probably true about the probability of seeing 3 out of 5 people have the degree? Relative to this probability, it's probably less, right? Right? Think about it this way. If I'm flipping a coin, the probability that I get 50 out of 100 to come up heads is way more likely than 70 out of 100. And that's way more likely than 90 out of 100, right? As I move away from that kind of expected value, the probabilities of outcomes further from that value start to decrease. So at least we kind of can keep that in the back of our minds when we're computing these probabilities to identify any like egregious errors we make. So, you know, to finish this example up though, right, we would just plug these values in. Now it's just a matter of getting comfortable using our calculator, being able to enter in the binomial distribution function. Okay. Any questions on anything that I've set up to this point? So we talked about a couple of these issues. We could do the same thing with 4. I'm not going to waste time on this because I want to bring something else up before we end the class today. So it's the same. Okay, if I wanted to find out probably that 4 people have a college degree, Literally nothing changes up here other than X becomes 4, right? And it's the same procedure. It's not wildly interesting, but here it is. So I don't know why I gave 2 examples that were so close, but I did. So I think it's because the next question I have, yeah, this is why. So I wanted us to have those 2 values just to save us time if we were computing it. But what if I wanted the probability of at least 3 out of the 5 having a degree? So what I want is the probability that X is greater than or equal to 3. Well, it's the same idea. Remember when I started out saying anytime we have this idea of being cumulative, and this isn't cumulative like going, it's actually like the complement, right? It's going in this value and above, but it's the same idea. I can only see 3 out of 5, or exactly 4 out of 5, or exactly 5 out of 5 people have a college degree, right? So there's no overlap. These are mutually exclusive outcomes. So if I think about every outcome that fits this criteria of this event A that I'm interested in, I'll just be taking the probability it's equal to 3, plus the probability it's equal to 4, plus the probability it's equal to 5. And basically I know when to stop because I'll stop at the number of trials, right? When it's kind of open-ended and being above this value, the highest possible number of successes I could see are whatever my number of trials. Any questions? Yeah.
So like, could you do the same thing where it's like, oh, so that you only have to do 2 things, if you do X equals 1, X equals 2, and just do 1 minus that?
See, you're just too smart. You're thinking ahead of this, right? So, no, I'm joking. I guess you're thinking about it right. So basically, I'll address it in 1 second. Yeah, one time. So I basically would have to use that binomial distribution function 3 times and add it up, right? So what you're saying is, well, look, what if I did 1 minus the complement of this event, right? That might save me some work. Oops. Right? Because now I might have fewer outcomes. You're close, but you forgot about one of the outcomes. Because what this is actually saying is the probability that, what's the first value for X I can see that meets that criteria? So yeah, the lowest one would be X is equal to 0, X is equal to 1, and actually X is equal to 2, right? Because it's less than 3 and it's a streak, so the very first one would be 2. So it doesn't really save me a lot of work here, but you're right. What if I wanted the probability that it's greater than or equal to 1? Well, then I have to probably it's 1 plus 2 plus, I have to use that binomial function like 5 or 6. Well, no, you actually could just find 1 minus the complement. The only X value that would meet this criteria is X being 0. You don't have to use that binomial distribution function 1 time. Okay, so we'll start to exploit that complement rule a lot, especially when we start talking about not just the binomial, but the Poisson distribution. So Monday, we'll kind of pick back up, do a little bit more discussion of the binomial distribution, introduce the Poisson distribution. And then probably Wednesday, we'll do maybe that one continuous distribution I mentioned. And then Friday, we'll do some review. And tentatively, I'm planning on, I said I was going to move that date of that exam up. Tentatively, it'll be that Wednesday of the next week. So that would be the 29th, if I'm doing that in my head.
Oh.
So we've got a little bit of extra time. We'll be able to get some review in, and I think that'll work out good. Okay?
Well, then one of them, yeah.
Any questions for me before I let you guys get out of here? All right, we'll see you guys on Monday. Have a good weekend.